All right, good afternoon, guys. So today we will, where did we stop? We stopped here, I think. I left this as an exercise. It's actually, so I have just posted a couple hours ago the second assignment. The deadline is in 2 weeks because there is not going to be an assignment next week. Next week we only have class on Thursday, and I will start talking about graph isomorphism, but there won't be exercises about that topic, at least not until the following week. So there are 8 questions, I think, in the second assignment, but you guys have 2 weeks. And as was the case with the previous assignment, some questions are supposed to be easy, some questions are supposed to be a little bit more difficult. This, for example, is one of the questions in the assignment. This exercise 1.39, okay? Hold on a second. So the class today, I want to discuss these eigenvalues of some classes of graphs. That will be the beginning of the class, and then there will be some. Let me get here. I added a couple new sections, and I have just updated the course notes on the website. There are a couple results here about the largest and smallest eigenvalues of a graph in this section, subsection 1.5. There's a nice result about regular graphs in this 1.6. And there are nice results about graphs with the largest eigenvalue smaller or equal than 2. This is 1.7. So this is all supposed to be the topic of today's class. I'm pretty sure I won't be able to cover everything, but I will possibly choose some of the things to discuss and see how we go. Okay, but the first topic, which was already prepared and planned for today, is this discussion on how to compute the eigenvalues for some classes of graphs. All right, classes that you guys should know about. So we have the complete graphs on n vertices, and hopefully you guys all remember. These are all the n vertices. Everybody is a neighbor of everybody, blah, blah, blah. You have everything, all right? K and M, actually, let me use AB because I just fixed the course notes on the website and I'm using AB. So these are the graphs with A vertices on one side, B vertices on the other, and you have all edges. So you have A vertices here, B vertices here, and all the edges between them, but no edges here, no edges here. All right. The cycle graphs on n vertices. So, right? And the path graphs on n vertices. So you have also n vertices, blah, blah, blah. So what I want today in the beginning of the class is to tell you guys how to compute the eigenvalues of these families of graphs in terms of n or a and b. Of course, here a plus b is equal to n, right? So for the complete graphs, it's actually quite easy because the adjacency matrix of the complete graph is the all ones matrix minus the identity matrix. And it's, so these two matrices commute, right? So J times I, of course, is equal to I times J. So it's, we know that there is a common basis of eigenvectors for J and I, and the eigenvectors of J, or at least the eigenvalues of J, are very easy to compute because J is the all ones matrix. So of course the all ones vector is an eigenvector, and the result is n, which means that n is an eigenvalue of J. Well, this is a matrix J has rank 1. All rows are equal, which means that only one eigenvalue is different than 0. All of the other eigenvalues are equal to 0. So the spectrum of the matrix J, the all ones matrix n by n, is n and 0 with multiplicity n minus 1. Therefore, the eigenvalues of J minus I are going to be n minus 1 and minus 1 with multiplicity n-1. All right. Any questions? And you have and you can of course find a basis of eigenvectors. You know that the all ones vector is an eigenvector, and you know that all other eigenvectors are all the other eigenspace is the space which is orthogonal to the all ones vector. So the set of all vectors whose entries sum to 0. All right. Can you repeat why we know all the other eigenvalues are 0? Because J has rank 1. All rows are equal. So therefore, anything which is orthogonal to the all ones vector, which is the same thing as the first row, will belong to the kernel, and therefore will correspond to the eigenvalue 0. And you have exactly a subspace of dimension n-1, which is orthogonal to the all ones vector. All right. So this is the spectrum of the complete graphs. Right. So the complete graphs are also essentially the only graphs that contain only 2 distinct eigenvalues. Because after all, the diameter of the graph plus 1, is limited above by the number of distinct eigenvalues, as we saw. And if there are only 2 distinct eigenvalues, the diameter must be 1, and therefore the graph must be complete. So with that, I'm also proving that the complete graphs are the only graphs with 2 distinct eigenvalues, and the eigenvalues are n-1 and -1. Let's move forward. So this is the now KAB. So this is the adjacency matrix of the complete bipartite graph, which means that I have A vertices on one side, B vertices on the other, and all the edges between them. So when I write the adjacency matrix, I am assuming that these first rows correspond to all vertices on this side. Therefore, there is no edge between them. So you have a block of zeros. This is a block of a bunch of zeros. The last rows and last columns correspond to the vertices on this side. So, of course, again, yes, exactly. I'm answering to the question on the chat. Yes. So this block here, okay, corresponds to the fact that there are no edges in here. So I'm simply listing all the vertices on one side and then all the vertices on the other, and I have these blocks of 0. And because I have all edges between them, this thing here is a block of 1s. A block of 1s of dimension A by B, which I'm denoting by this. So I'm using the notation that JAB means that you have A rows, B columns, and you have 1s everywhere, right? So because they're all edges between these guys, you have 1s everywhere. Everything on the left is a neighbor to everything on the right. And then, of course, here you have the transpose, which has the different shape, right? So B rows and A columns. Now, how many vectors are there in the kernel of JAB? Linearly independent. So this has B1s. If I multiply JAB by something, and I get 0, the 0 vector, it means that all the entries of this vector sum to 0. This vector has B entries, so there are essentially B minus 1 vectors, linearly independent, which if I multiply by this JAB, I get 0 on the right. And there are A minus 1 vectors, all of them linearly independent. If I multiply JBA by this guy, I also get 0. So there are b minus 1 linearly independent such vectors. And here there are a minus 1 linearly independent such vectors. Right? So what happens now is if I take A and I multiply A by U and then V, a big vector, the result here is going to be JBA times V on the top and JAB times U on top. Nope, sorry. It's going to be JAB times V on the top and JBA times U on the bottom. And these two things are equal to 0. So if I consider all these linearly independent vectors and I concatenate with all these linearly independent vectors, right? I still get I get a basis for the 0 eigenspace. And for each one of these guys, I can take any one of these guys and I still have something linearly independent. So in total here, I have A minus 1 times B minus 1, which is AB minus A minus B plus 1 linearly independent vectors which belong to this eigenspace, to the eigenspace that is equal to 0. Does this make any sense? Yes. What did I get wrong?
You multiplied instead of adding.
Oh, yeah, of course. Ah, you are correct. Why did I do that? I have no idea.
If you did that, you would have a linear independent set bigger than the dimension of the...
Yeah. I don't know where my mind was, but anyway, that's it, right? So I have all these vectors, and I can, and all this, all things of this form are working here. So I have the basis generated by these guys completed with 0, and the basis generated by these guys completed with 0, and all linear combinations of these things will be equal to this. So that's correct. Yeah. So I'm almost there, right? So n, which is the dimension of the space, I have almost found n linearly independent eigenvectors. I need to find 2 more. And these 2 more, you can check, are going to be equal to this. Square root of b times the all-ones vector on the top, square root of a times the all-ones vector on the bottom. And these you can check now. So if you multiply a by this thing, square root of b, all ones, square root of a, all ones, what you get on the top is going to be JAB times the all ones vector. Let me put the square root of A, and here square root of B, JBA, all ones vector. All right, so this is what I get. So on the top, I'm gonna have square root of A. Now, JAB, each column has, each row has B1s, and I'm summing the number of ones in each row. So here I will have B times the all ones vector, and on the bottom I have square root of B. Each row in JBA has A1s, and I'm summing the number of ones. So I have A times the all ones vector. And now it's easy to see that this is giving us an eigenvector eigenvalue equation, because this number is precisely this number multiplied by the square root of AB, and this number is precisely this number multiplied by the same thing. So this this is an eigenvalue corresponding to this eigenvector, right? So this is equal to the square root of AB times exactly square root of B all ones, square root of A all ones of convenient size. So it's not difficult to check that this is an eigenvector with eigenvalue square root of AB. And because this graph is bipartite, we saw last class that if I now put a minus sign here and the entries corresponding to one of the classes, I also get an eigenvector whose corresponding eigenvalue is minus the corresponding eigenvalue of this guy. So I have eigenvalues square root of AB and minus square root of AB corresponding to these two vectors each. And these allows me to complete my quest for finding enough eigenvectors. I had already found A plus B minus 2 eigenvectors, linearly independent eigenvectors. Now I have just found the 2 remaining. Any questions? Moving forward. Now I want to compute the eigenvalues and eigenvectors of this hypergraph. I will need to use complex numbers. Hopefully this is not going to be too complicated to you guys. But if this is too much, do not worry. It's not such a big deal if you do not follow this one. So the adjacency matrix of the cycle on n vertices is the sum of two permutation matrices corresponding to the permutation that maps 1 to 2, 2 to 3, and n to 1. So this permutation, this is a permutation matrix 1, 1, 1, 1, 1, 1, 1, 1, plus this permutation 1, 1, 1, 1, 1, 1, 1, 1. These two things added to each other give you the permutation matrix of the cycle on n vertices, right? Now, an eigenvector and these matrices are cyclic in the sense that if you compute powers of this matrix, you will be generating permutations which are mapping now. So if you take this matrix as squared, I will be taking the matrix that maps 1 to 2 and 2 to 3. So the matrix that maps 1 to 3 and so on. So this matrix here, P, if you write P squared, the answer is going to be the matrix that maps 1 to 3, 2 to 4, and so on. So it has this, it's going to be like that. And here there's going to be ones like this. And the rest is a zero. Zeros. And if you keep taking powers of these matrices, you will see that this diagonals of ones is going down, and this diagonals of ones are going down like that, and getting bigger and bigger. So this is what happens with the powers of cyclic permutation matrices. You can check. An eigenvector for a cyclic matrix can be easily built from a n root of unity. This is the complex number, so that omega raised to the power of n is equal to 1. Why is that? Because if I multiply p by this vector, the answer that I get is this vector here. I'm rotating this vector. I'm making this vector go, I'm cycling, right? I'm rotating this. So each one of these entries is going down and this one is going up. But then it's not difficult to realize that from this vector to this vector, you can get there by simply multiplying by this number. And similarly for the transpose, P transpose or P inverse, except that this is the eigenvalue. So what you're getting here is that this guy is an eigenvector for P plus P transpose. And the eigenvalue is omega plus omega to n minus 1. And this is the adjacency matrix of the cycle. So I have just found a bunch of eigenvectors, each one of them corresponding to this eigenvalue. Now, interestingly, these numbers are all real because omega to n minus 1 is omega conjugate. Therefore, this thing here is 2 times the real part of omega. Okay? And this n roots of unity are all of the form e to the 2 pi I k over n, for k varying from 0 to n minus 1. And therefore, this real part is going to be the cosine of the angle. And these are exactly the eigenvalues of the cycle. Okay? It's not too difficult for you to check that these eigenvectors are all going to be orthogonal to each other if you pick different roots of unity. Okay? But that I will leave as an exercise. And this is basically saying for when k is equal to 0, this thing here is equal to 0, the cosine is equal to 1, and therefore 2 is always the largest and simple eigenvalue of the cycle, as you would expect. The cycle Cn is a 2 regular graph. This is 2 regular. The all ones vector 1, 1, 1, 1, 1 is an eigenvector. It corresponds precisely to the situation here where omega is equal to 1. 1 is a root of unity. 1 raised to the power of n is equal to 1 for all n. Right? So indeed we find 2 as the largest eigenvalue corresponding to the all ones vector. And you also find that minus 2 is going to be an eigenvalue if and only if n is even, corresponding then to when k is equal to n minus 2. Because when k is equal to n minus 2, this thing here is pi, the cosine of pi is minus 1, and minus 2 is going to be an eigenvalue. If n is not even, then this cosine can never be minus 1. Minus 2 is not an eigenvalue, and in fact the graph is not bipartite. Question on the chat, is it possible to write bases to the eigenspaces using only real vectors? Of course. Because if you replace omega by omega to n minus 1, you also get an eigenvector to the same eigenspace. And now you can simply, instead of using 1, so you can combine this guy and this guy. It's conjugation, right? This operation here is conjugation. So it's simply conjugating. So in fact, you can pick, let's call this vector v. Instead of using v and v conjugate, you can use v plus v conjugate and v what can you do? V plus V conjugate and the conjugate of V minus V conjugate. So the real parts and the imaginary parts of this guys.
You're conjugating the whole number. So if it was imaginary, it would be still, you'll have an imaginary part after.
Yeah, okay, so probably I want to take this is fine, so I want to take the imaginary part of this, right? Yes. Okay, it's probably what I want. Yeah.
I times that, right?
The imaginary part is already without I.
You know, like when you are subtracting, you're like transforming all the real parts into 0, so you can multiply by I.
Yes. So what am I doing? No, it's all fine. It's all right. So I want the imaginary part of this thing.
Yeah.
Yes. It's all good. So yes, you can do that, of course. But I mean, you do not need to. Well, you can go through here, through this path, and this is good. But you can also simply believe that because you have real eigenvalues, you can simply, well, you can always diagonalize a matrix, right? You can solve you can find the eigenspaces by Gaussian elimination, right? So that's also possible. Of course, this gives you more conceptual information, but is certainly less. I mean, it's less elementary, this understanding. But this is all fine. And this gives you the full spectrum of the cycles on inverses. So we do know that the cycles have these eigenvalues, and we know how the eigenvectors look like for each one of these eigenvalues, right? For the path graph, the path on inverses, how do you find the eigenvectors and eigenvalues? So I will provide one way now, the other will come later. Look at the cycle, okay, which contains 2n plus 2 vertices. So this is the cycle. Okay, and assume, oops, let me do it like this. Assume that there are n vertices here, n vertices here, okay? Plus this one, plus this one. 2n plus 2 vertices. Now, if omega is a 2n plus 2th root of unity, then these guys are both eigenvalues for this matrix, for this are both eigenvectors for this matrix, for this eigenvalue. And so is any linear combination of them. In particular, if I take these two vectors and I make this one minus the other, I get this as an eigenvector. This is an eigenvector for this eigenvalue in this matrix. And it's not difficult for you to see that also here in the position n minus 2, n plus 2, there also will be, the thing will be equal to 0 here in this position, corresponding to this guy. So this vector here has 0 in the first position, a bunch of things, 0 in the n plus 2 position, and then a bunch of things. So this is basically saying that the eigenvector which assign to this vertices 0, a bunch of things, 0, and a bunch of things, is an eigenvector for this graph. Now, it's not difficult for you to see that you can now simply look at the eigenvector eigenvalue equation for this part of the graph. So this n non-zero entries from positions 2 to n plus 1 are part of an eigenvector of this graph, which do not get interfered by the rest of the graph, because those zeros at positions 1 and n plus 2 disconnect the eigenvector. What do I mean by that? When you multiply the adjacency matrix by this big vector, right, and you look at this particular entry, it will be the eigenvalue times the value here equal to this guy plus this guy, but this one is 0. When you look at this entry and you multiply by the eigenvalue, it's going to be this guy plus this guy, and I'm good to go. And when I look to this last one here, multiplied by the eigenvalue, the result is going to be 0 plus this one. So in fact, just this part here, ignoring those zeros, is an eigenvector for the smaller graph that you find here. So this is an eigenvector for the path on n vertices, which is exactly what I see here, n vertices. Okay. So this part of the eigenvector is also an eigenvector for Pn. And therefore the spectrum of the adjacency matrix of Pn is omega plus omega minus 1, which is equal to this, which is exactly the eigenvalue we had. Recall now that omega is not the nth root of unity, is the 2n plus 2th root of unity. Right, so omega is 2 pi I k over 2n plus 2. All right, that's why 2 cancels here, and you're summing with the conjugate, and this is what you get, this cosines, 2 times this cosines. For k, of course, from 1 to n, because for k equals 0, you do not get the zeros appearing, right? So you are able to find the eigenvalues of the path by examining the eigenvalues of a bigger cycle, finding eigenvectors with 0 positions, disconnecting the bigger cycle, and seeing what you have. All right. All of these eigenvalues are simple. All of them are simple. So you do not need to worry, meaning they have multiplicity 1, and you have just found enough of them. So you do not need to worry whether or not you still need to try to find more eigenvectors, or if the eigenvectors were orthogonal or not. You have just found n eigenvalues of multiplicity 1, so this is a complete diagonalization. The path has only simple eigenvalues. All of them lie between 2 and minus 2. Because these are all 2 times the cosine of things, and these things are never 1 and minus 1. Any questions? Now, I've shown you guys these 2 things. I do not expect any of you to feel able to come up with this idea on your own if you had to, okay? So this is more of an expository technique on how to find eigenvectors and eigenvalues of graphs. See that for all these 4 cases, I never ever try to write the characteristic polynomial in terms of a determinant, compute the roots, and then solve the eigenvectors. Always, it's very rare that if you want to find the eigenvalue of a graph, you will try to do that. Most likely, you will be always trying to construct an eigenvector. You build your eigenvector, you look at the graph, and then you try to adjust and find the eigenvalue. Okay, so for this case, is everything worked out? In general, if you pick a simple enough family of graphs, you can at least find some eigenvalues and eigenvectors, but this is in general, of course, not so easy. Forget about this exercise 1.40. This is, we just did it. This was letter B. Okay. This is probably a good moment for me to stop for a couple minutes and ask if you guys have a question, and we can resume in 4 minutes. So you guys have a short break, get a coffee, a cup of water, or whatever. You guys have a question? No questions? All good? You guys could have questions about other things as well, the assignment or whatever. So what is the goal with all the things we have been doing so far? It's to get accustomed to techniques and results, and well, it's basically to get used to think of graphs and picture what can you tell, or if you can compute, or what kind of information is contained on the spectrum, right? So it's also a common problem in spectral graph theory to try to characterize and describe the families of graphs whose eigenvalues or eigenvectors lie within a certain interval. So ideally, we would like to have a result that says all eigenvalues, all graphs whose eigenvalues lie between, I don't know, -10 and 10 look like this. And unfortunately, this is not possible in general, but we can do a certain damage for small values, small integral values. And one of the earliest results And spectral graph theory is a full classification of all graphs that have largest eigenvalue at most 2. We have just seen a couple, the cycles and the paths. Right? The cycles actually do have a largest eigenvalue equal to 2, and the paths have largest eigenvalue smaller than 2. So we would like to know what else, which other graphs do satisfy this, okay? Now, the first lemma kind of ties with the topic of last class, and it's a result which is typically stated as part of the Perron-Frobenius theory, except that I didn't. I left this result for today's class. And the result is this. So if you have G, a connected graph, and if you take any proper subgraph, meaning either you remove edges or you remove vertices or both, but you have to remove something, then as long as, well, G is connected, you can guarantee that the largest eigenvalue of the subgraph actually decreases. And I'm leaving this as an exercise, but I am going to give you guys a hint, right? So the hint is take V. First, assume that you can start by doing that. Maybe it's easier, maybe it's not, but you can decide for yourselves. Start assuming that H is a spanning subgraph. Spanning means same number of vertices, fewer edges. So H, same vertices as G, but fewer edges. Fewer edges. Assume, so I'm using this notation, lambda of H to denote the largest eigenvalue. So assume H times V is lambda H times V. So what do we know about this vector V? We learned last class that lambda of H is positive. V is a vector with positive entries. Well, as long as H is connected. So maybe H is not connected. But we know that this is at least non-negative. Yes. So you can always assume that this is non-negative vector. And in fact, yes, so you can always assume that V is non-negative because H could be disconnected, right? And the largest eigenvalue of this graph will be the largest eigenvalue amongst all the largest eigenvalues of the connected components. And then you simply take the eigenvector for that connected component and you make it 0 everywhere else, right? So you know that this is true. Now the question is, what happens if you multiply, if you consider the Rayleigh quotient of V according to the adjacency matrix of G? So this is the sort of thing that you should be thinking about. Okay, and the idea here is that so for example, if H is connected, then we actually know that V is positive, and then it's not difficult for you to realize that this cannot be, that this actually is bigger, strictly bigger than the Rayleigh quotient of V in the adjacency matrix of H. Because you will be summing more things here than you are here, because there are more edges in here. Right, recall that the Rayleigh quotient of a vector according to the adjacency matrix of a graph is the sum for all I neighbor than J of Vi times Vj. So if there are more edges in G, then you will be summing more things which are positive. Now, if H is not connected, then this guy is greater or equal than 0, but you can still kind of find a vector instead of V to put here that will ensure that this Rayleigh quotient exceeds this guy. Okay, so think about this. This is the sort of idea you should be trying to work in this question. I'm leaving this question actually, so this question is in the assignment. This is possibly one of the most difficult questions in the assignment because you need to check all these details carefully, all right? So this, I'm assuming H is a spanning subgraph with the same number of vertices and fewer edges. After you have finished this, then you can now assume that H has fewer vertices. Then you can assume that H is an induced subgraph of G. Meaning now that you are looking at the full G and you are selecting a subset of vertices, but you're not discarding any edges. If H is an induced subgraph of G, then how can you show that the largest eigenvalue of H is smaller than the largest eigenvalue of G? Same trick. Consider an eigenvector for the largest eigenvalue of H, pad it with zeros, compute the Rayleigh quotient, tell me what you see. Compare with the Rayleigh quotient of that same eigenvector at G. All right. And then if you have done these two cases, the other cases are taken care of, because now if you take any graph which is a subgraph of G, and this is neither spanning nor induced, it is always going to be a spanning subgraph of an induced subgraph. So if you take now any H subgraph of G, first you get G, select the induced subgraph by the vertices of H, and then you remove a couple edges. So you're going to have a spanning subgraph of an induced subgraph. So any subgraph of G is a spanning subgraph of an induced subgraph. And if every time you take these operations, you're reducing the eigenvalue, you will be reducing the eigenvalue in the end. All right? So try to make sense of this. I think this is a very nice exercise to understand what's going on. All right. So I really want you guys to, all of you, to first try to do this on your own. And if you get stuck, talk to me, ask a question, and or discuss with your colleagues and see what happens. All right. But it's very important that you actually write this proof on your own. Now, with this, assume that this lemma has been shown, that you're satisfied with it. Why is it true that any graph with largest eigenvalue 2 is either a tree or a cycle? Why can it not be a graph that contains a cycle? Why can't this be a graph with eigenvalue 2? Maximum eigenvalue 2. Because of this lemma, right? This cycle here is a subgraph. This cycle on its own has largest eigenvalue 2. Therefore, the largest eigenvalue of G must be strictly bigger than 2. So if the graph contains a cycle, but it's not a cycle, its largest eigenvalue is bigger than 2. Therefore, any graph with largest eigenvalue at most 2 is either a cycle or a graph without a cycle, ergo a tree. Now, show that the following graphs all have largest eigenvalue equal to 2. So you have one graph here, one here, one here, right? So you have 1, 2, 3, and then this is a family, infinite family of graphs, which you obtain by having these two leaves, and then either a vertex or two vertices or three vertices, or in general, a path. All right? So here in this drawing, there are infinitely many graphs. 3 of them are sporadic, and the others form an infinite family. And I want you to show that all of them have 2 as the largest eigenvalue. And you should be able to do that by exhibiting a suitable eigenvector. So I truly want you to come here and guess what the eigenvector would look like. For example, if this is 1 and 2, so this is the entry of the eigenvector corresponding to this vertex. If this is 1, what should be the entry here? Now, how could I possibly know that? Because of this. Imagine that this is vertex u. So I know when I multiply a, let me call this vertex a perhaps. When I multiply a by the eigenvector v, and I get 2 times v here, I'm going to examine only the row corresponding to vertex a. So on this side, I have the sum of the neighbors of A of their entry in the eigenvector. And on this side, I have 2 times the 8th entry in the eigenvector. A only has one neighbor. Let's say this is vertex B. So I should have probably written like that. I don't know. W neighbor of A. So this thing here is the bth entry of the eigenvector. If this is 1, then this is 2. So if this is 1, this is 2. By symmetry, if this is indeed going to be an eigenvector, I know that whatever comes from the, well, other sides could be the same. So I could guess now. Because see, if I, no, actually I could, what could I do? I could guess the value here, because I can examine the eigenvector equation for B. So 2 times 2 is going to be 1 plus 3. Yes. Now for this one, it's not so easy anymore, because what's going on? 2 times 3 is 6. So I know that this guy plus this guy is 4. And then I look at this drawing and I think, okay, now listen, if I put 2 here and 2 here, I'm good to go. And I know that this should work with 1 and 1. So that's it. Done. This is an eigenvector for the eigenvalue 2. How can I actually show that 2 is the largest eigenvalue? What guarantees that I cannot find an eigenvalue bigger than 2 for this graph?
The largest eigenvalue is associated to an eigenvector, an positive eigenvector.
Exactly. The only eigenvalue that contains an eigenvector with all entries positive is the largest eigenvalue, and I have just found an eigenvector with all entries positive. Watch out, Danielle. what we know is that if the graph has a cycle, its largest eigenvalue is bigger than 2. We have not proved yet, and it's in fact it's not true that if the graph does not have a cycle, its largest eigenvalue is 2. That's actually false. Okay. So yeah, great. But this is what we have. We know that 2 is the largest eigenvalue because this is a positive eigenvector. So that's it. Great. I managed to come up with an eigenvector and it worked. What is going to be the eigenvector here, 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 and in general for this family? So this is an exercise for you guys. And in order to show that 2 is the largest eigenvalue, this eigenvector you already know has to be positive. And you can always start from the leaves and try to slowly but surely construct the eigenvector. All right. Now, from this previous exercise, it follows that any graph with largest eigenvalue at most 2 is either a cycle, one of the trees above, as you see, these are all trees with largest eigenvalue 2, or possibly a tree which has not been drawn here, but this tree cannot contain any one of these trees as a proper subgraph. Because if it did, then its largest eigenvalue would be bigger than the largest eigenvalues of these trees, and choose the largest eigenvalue of all of these trees. Now, not containing any of these trees as a proper subgraph already tells you that no matter which tree has eigenvalue bigger than at most 2, it cannot contain a vertex of degree 4, for example, because if this tree, very big tree here, contain a vertex of degree 4 somewhere, then this whole tree here would be a subgraph of this one. So we have found a couple trees with largest eigenvalue 2, and we know that no other tree that has largest eigenvalue 2 can contain any one of these as a proper subgraph. So I know that there is no tree with a vertex of degree 4, because the only tree with a vertex of degree 4 that has 2 as the largest eigenvalue is this one. I also know that it cannot contain two vertices of degree 3, because otherwise some of these would be a proper subgraph. If I draw here a big tree, and this vertex has degree 3, and this vertex has degree 3, I can simply consider now the path that goes from one to the other, even if there are other things here in this tree. This guy here, right, would be precisely one of these. So now I know that if there is any other tree with largest eigenvalue 2, it can only contain at most one vertex of degree 3 and all of the other vertices of degree 2 or 1. And then it's not difficult for you to see that these 3 examples here above actually seal the deal. All right. No tree with more than the number of verses you are seeing here can contain a vertex of degree 3 without containing any one of these as a proper subgraph. So the only graphs that remain are the subgraphs of these. So the only trees which have not been accounted for yet are the subgraphs of these. So for example, you have the paths. The paths are subgraphs of these guys. Or the star, which is either a subgraph of these or a subgraph of these. So the conclusion is The graphs with largest eigenvalue at most 2 are either cycles or trees. And if the graph is a tree, it is either one of these or a proper subgraph of one of these. So those have been completely fully characterized. You have a finite number of examples and an infinite family, and the paths on n vertices, or the paths with 2 vertices in the end like that. All right. Now it's also a famous theorem which I would not delve into, a full characterization of the graphs whose smallest eigenvalue is -2, and it's in fact a field of research in spectral graph theory. Any attempt to characterize all graphs with the largest eigenvalue or smallest eigenvalue bigger than something smaller than 2 or smaller than something bigger than 2. It's, as far as I know, there is no full characterization of how all graphs with smallest eigenvalue bigger than -3 exist. So these things are not easy at all. It truly consists into examining things and finding some examples, but only for largest eigenvalue 2, it's as simple as you have just witnessed. All right. Another theorem that I'd like to discuss today is perhaps the first result I'll show you guys, which is non-trivial and relates eigenvalues to a NP hard parameter. So given a graph, one could be interested in finding the largest possible independent set, or co-clique. So a co-clique is a set of vertices, none of which is a neighbor to the other. So this thing has 3 names. All the names equivalent. It depends with whom you're discussing graph theory. So independent set, this is possibly the most common. Stable set and co-clique. Typically, graph theorists will use this one. People that work with graph theory, really pure graph theory. This is typically coming from the optimization people, and this is typically for spectral graph theory people that do spectral graph theory. So, of course, I prefer to use co-clique. Why co-clique? Because clique, this one is kind of a consensus. Everyone, when they speak of a clique, they mean typically a subgraph, a complete subgraph. So a co-clique is the complement of a complete subgraph. So the complement of a clique is a co-clique. But you will see people referring to these things as either independent set, stable set, or co-clique. The size of the largest such thing that you can find in a given graph is always denoted by alpha of G. Alpha is always the letter, and this is either the independence number, the stability number, or the co-clique number of the graph. Depends on whether you use independent, stable, or co-clique. Okay? So you can choose either one of these names. The symbol, however, is always alpha of G. Alpha of G is the size of the largest such thing you can find in a graph. Now, this parameter is very difficult to compute, meaning that if I give you a graph, randomly generated graph with 3,000 verses, most likely you will never know what is alpha of G, because the complexity of computing this thing rises exponentially if you want to compute it exactly with regards to the size of the graph. And it's been shown that if there is a polynomial time algorithm to compute this thing, then P is equal to NP. So computing this parameter in polynomial time is NP hard. Sorry. Computing this parameter in polynomial time is most likely not possible. And computing this parameter is as hard as resolving any other problem in the class NP. So why am I saying all these things? Because it's also a topic, a field of research in spectral graph theory / optimization to find upper bounds or lower bounds to these parameters, which can be obtained by examining easily computable things in the graph. Because the more bounds you know, more likely you will be to actually show that whichever co-clique you found is as big as possible, right? So for example, if I know that this thing is at most something and I'm given a graph and I compute a bunch of these guys and suddenly I find something which is as big as this, I know that I have just found the solution, right? So there is a sort of motivation to find upper bounds or lower bounds for these numbers in terms of easily computable things. And one of the oldest known upper bounds, useful upper bounds for alpha of G is obtained by means of eigenvalues and eigenvectors of graphs. So this is the result. If G is a k-regular graph, so this only works for k-regular. If G is not k-regular, then, well, there are certain things you could do, but the formula is never going to look as nice as this one. So if G is k-regular, the eigenvalues, I'm listing the eigenvalues from bigger to smallest. Of course, as we saw, the largest eigenvalue is the valency, corresponding to the eigenvector of all ones. Let's use alpha to denote the size of the largest co-clique of G. Then we can show that alpha is upper bounded by this thing. Now, does this bound make sense? Yes, it does. Why? Well, this is positive. This number is negative. So this is positive minus negative. So it's positive plus positive. This is the number of verses in the graph. This is negative. So minus it is positive. So I'm fine. This is a positive number at least. I'm not saying that alpha is smaller or equal than something negative, which would be a problem. And not only that, well, I have this thing, which is positive. Here I am picking something bigger than it. So this fraction is smaller than 1. So I am taking a fraction of n. So it's not that bad. I'm basically dividing n by something. So this is a fraction of n. So not that bad, as I would expect. So if I had written here an upper bound alpha smaller or equal, then if I had written here something bigger than n, you would say, of course, the largest independent set in the graph, the largest co-clique in the graph, of course, is at most the number of verses in the graph. But I'm good. I'm actually writing here something which is potentially smaller. Okay. Now, how do we prove that? Is actually there are several proofs of this fact, and this is my favorite because to me it's conceptually the simplest. So let X denote the characteristic vector of the largest co-clique, meaning that I have a vector with n entries, right? And if this is my graph and the largest co-clique has a verses 1, 3, 5, 6, and 8, I'm gonna come here and put 1, 0, 1, 0, 1, 1, 0, 1. So I'm putting ones in the entries corresponding to the verses in the co-clique and zeros everywhere else. Okay, so this is the vector X. And when I do this, I typically use this name, the characteristic vector of the subset. Now this is the idea. Why is this true? The thing is, when you multiply A by X, the result is a vector, and this thing is a sum of the vectors corresponding to the neighbors it's difficult to write with this thing, shit. Corresponding to the neighbors, oh my god, again, to the neighbors of the vertices in the co-clique. Now, it is very important at this point that you truly understand why this is true. It's just matrix multiplication. When I multiply A by a vector that looks like this, 1, 0, 1, so let's assume that here I have A, this is A, multiplied by 1, 0, 1, 0, 1, 1, 0, 1. Right? So this is 1 times the first column of A, 0 times the second column of A, 1 times the third column of A, 0 times the fourth, and so on, and you add all these columns. That is a linear combination of the columns, and the coefficients are exactly the numbers that appear here. So you are summing the columns that correspond to the neighborhood of each one of the verses in the co-clique. So I'm summing this, right? This, with this, and so on. When I take the inner product, I'm basically asking which ones of the vectors in the co-clique belong, or how many of the vectors in the co-clique belong to the neighborhood of any other vertex of the co-clique? And the answer is none. No vertex of the co-clique is a neighbor of any other vertex in the co-clique, because that is the definition of a co-clique. None of these guys are neighbors to any other. So the intersection between the co-clique and the neighborhoods of the vertices in the co-clique is 0. And this is exactly what this equation is saying. Now this is where combinatorics meets linear algebra. Okay? As a consequence, if I replace this matrix in the middle by this, X transpose AX is 0, so the only thing that remains is X transpose times I times X times this number, and this is the result, because after all, X transpose X is equal to alpha. It's the size of the subset. On the other hand, I can rewrite this product by expanding and obtaining the spectral decomposition of this matrix. And the spectral decomposition of this matrix is the spectral decomposition of A with the same eigenspaces, however subtracted each one of the eigenvalues by lambda n. Right? After all, A is equal to the sum of lambda I e sub I and I is the sum of E sub I. So this matrix minus lambda n times this is exactly what you see there. It's exactly this. Now, all of these things are non-negative. Why? Because lambda n is the smallest eigenvalue, so I'm always subtracting the smallest eigenvalue from all of the other eigenvalues, so these are always going to be positive, or at least non-negative. And these things are the lengths of projections we saw last class. X transpose E sub I x is X E sub I transpose E sub I x. And this is always non-negative. So this is a sum of non-negative things. And I can discard all of them but the first, and I have an inequality. So this thing that you're seeing there is greater or equal than lambda 1 minus lambda n x transpose E sub 1 x. I'm simply ignoring the smallest terms, the terms corresponding to bigger indices. All of them are non-negative, so if I throw them out, I get something necessarily smaller or equal, right? But I know which matrix is this. This is the all ones matrix. The graph is regular. Lambda 1 is the largest eigenvalue. It's equal to k. Its only eigenvector is the all ones vector. The projection onto the all ones vector is the all ones matrix scaled. Right? The normalized vector is 1 over square root of n. This is the normalized vector corresponding to k. The projection onto the eigenspace here is 1 over square root of n all ones times 1 over square root of n all ones transpose. So this is 1 over n, 1, 1 transpose, which is 1 over n all ones matrix. Right? And then it's not difficult for you to realize that if you have a 0, 1, 1, 0, 1, 0, 1, whatever, and then here all ones matrix, and then here 1, 0, 1, 1, 0, 1, 0, 1, or whatever, the result here is the number of ones in the block corresponding to these rows and the same columns. So I erase the rows that contain a 0. So I erase this, or whatever. I erase the columns that contain a 0. Oops, I erased too much. I erase the columns that contain a 0. And I end up with a block of ones here. And the result is the number of ones in the block of J corresponding to the co-click. And the number of ones in this block is the size of the co-click squared, because I have number of rows, number of columns equal to the number of verses in the co-click. And that's what I get. This thing here is equal to this. And now you simply rearrange things and you get exactly the upper bound we wanted. All right. So I'm not sure about you guys, but I look at this and to me this is poetry. It's very simple, very elementary. It gives you something, and you know what? You know why this is so amazing? Because there are many graphs that actually meet this bound with equality. Many graphs meet this bound with equality. Okay. So this is not a naive thing in the sense that this actually makes sense for several families of graphs. Of course, in general, you should not expect this bound to be very good because after all, computing alpha is NP hard and computing these eigenvalues is not. So for a given random graph, this cannot be a very good approximation, typically. But there are many graphs for which this is a good approximation, or this is actually equality. So there are well-defined conditions for alpha to be met to meet with equality here. So for equality to hold here, you need, so where is the inequality? The inequality is here, right? So this is the moment that I threw things out anywhere and I created an inequality. So equality is met here if all the things that I threw out are 0. So I know that some of these will be 0, those corresponding to when I is equal to n, or when I'm looking at eigenvalues which are equal to the smallest, this is 0. And these things I can throw out without worrying. I'm not losing anything. For when this is not 0, then I need this to be 0. So I know that what I can tell for sure is equality if and only if there exists co-clique so that its characteristic vector belongs to the space generated by the largest and the smallest eigenvalue, belongs to the space generated by eigenspaces corresponding to largest and smallest eigenvalues. Oops. So I know that this doesn't say much in the sense that this is not telling me combinatorially, and in fact, combinatorially, there is not really a good way to understand this condition, but this is a condition at least. So if there is a co-clique so that the characteristic vector of that co-clique belongs to the sum of the eigenspaces corresponding to the largest and the smallest eigenvalues, then the Delsarti bound holds with equality, and this is in fact typically referred to as a Delsarti co-clique. Yes, it can, Danielle, a question on the chat. This is better understood if you think of lambda I minus lambda n as the distance from I to n, to lambda n. So if this is negative, but this is more negative than this, and because I'm doing minus negative, I'm actually summing something bigger. Okay? This thing is bigger than this, if this is negative. This is bigger than the absolute value. Minus 3 minus 7 is 4. Okay? Daniel? Okay, I will trust that you got it. So this is the authority bound. And from the stuff that I actually wrote here, the only thing remaining is this 1.5, and I would not do it. So I will leave this for you guys to actually read on your own. Okay, your message is finally got through now, so I think I have some delay here on my chat, but yeah, okay, good, we got it. So this section 1.5, I will leave this for you guys to read. It contains 2 results on how to bound the best known bounds for the largest and the smallest eigenvalues of a graph. This probably shouldn't have a square here. For the largest and smallest eigenvalues of a graph, the largest in terms of the square root of 2m minus the number of vertices. So this is the best you can do if you are only using number of edges and number of vertices on to bound the largest eigenvalue, and also a lower bound to the smallest eigenvalue, which is minus the number of vertices over 2. Okay, so these are 2 simple results that allow us to bound up and down the size of the smallest and largest eigenvalues of a graph in terms of the number of vertices and edges alone. This is slightly more complicated proof, but it's nonetheless quite interesting. It uses Cauchy-Schwarz, so if you're curious, you should read it through. This one is more simple and actually quite nice as well. Because these are very ad hoc techniques, they would not eventually lead us to anywhere more deep than themselves. I will skip them. Next class, we will start talking about graph isomorphism. Okay, so I will improve the section on the course notes about graph isomorphism. Most likely, I will follow a completely different path than I did last time I taught this course. So hopefully, this is going to be a new, exciting experience to all of us. All right. So if you have any questions about these things, please shoot on Teams. I will be checking to see if you guys are, if you guys are trying to solve the new assignment and you want to ask any questions, please go ahead. The new assignment is due in 2 weeks. And we will see each other in 1 week. Okay, so good holidays for you guys.